I'm going to show you a very simple proof by induction of the scalar dot product. If you're not familiar with how to add and multiply vectors, then you might want to just go over the first couple of chapters of a good maths book on vectors, just to get, but it's really easy, so that'll only take you 5 minutes just to get the idea of what a vector is. What I'm going to do first is just show you how we get to this equation here. You can see this equation here says a dot b equals the magnitude of a times the magnitude of b times the cosine of the angle between these two. Now, what I can do is I can show you this first of all to show you that we can get the angle between these two vectors purely from a geometrical point of view. So this here is one of the vectors. It's 4i so that we're going to use an example of this vector a being 4i add 3j, and then this vector b being 10i add 50j. So we've got two vectors there, and I've drawn them in the same xy region. Now, the total angle of b is phi here, and the angle of the vector a is theta, and then we've got this angle between these two vectors, and I've designated that as gamma. Okay, so you can see from a geometrical point of view that that angle minus this angle, so the angle of the vector b to the x-axis minus the angle of the vector a, theta, to the x-axis, is equal to gamma. So you can see that that's the angle between these two vectors, gamma. So we can just solve that geometrically by just going that gamma is, as I've said, this angle minus that angle, and so we can, first of all, we know that the magnitude of a, so the magnitude of this vector here, is simply 4 squared plus 3 squared square root of, which gives us 4 squared 16, add 9 square root, which is 25, square root of 25 is 5, so that gives us magnitude of a. And also we're going to find, for this we're going to find the magnitude of b as well, so the magnitude of b is 50 squared at 10 squared square root all of, that gave us 50.99. so we found the magnitude of that, found the magnitude of that. Now we know that this side here, this length here, although it's 4i, we can also say it's the magnitude of a times cosine theta. Remember that cosine theta is adjacent divided by hypotenuse, so we can write this down straight away. So we can write 5 cosine theta equals 4, and then we can solve for theta just like so. We could just rearrange the 4 on the 5 here like I've done, and then we take the inverse cosine in a calculator, we get that. We can do the same thing for this angle here. We know that again this magnitude here times the cosine theta is the same as, is equal to 10i, so we can do the same thing as we did for this one, and we rearranging we get phi equals the inverse cosine of 10 over 50.9, which is 1.3. So we found both phi and theta, and gamma then is just simply that minus that. So we take that, we minus that, which is down here, and we get the angle between the two vectors is 0.7299. Now I'm going to do it now the dot product way to show you sort of that the dot product is real, and will give you the same result. So here the dot product way of doing this is simply to multiply the two vectors together using the dot product here, and then we set that equal to the magnitude of them both times the cosine of the angle between them. Well, we're after, in this case, we're after this gamma, and we found it here, so we can find that immediately just by rearranging the equation. So we bring these two under here, we've got cosine gamma, we can then find the cosine gamma as 0.745244. So to get gamma we just take the inverse of that, so it's the cosine inverse is 0.7299. so you can see here by simply plugging in the values, using the multiplying the two vectors together and just multiplying the magnitudes and dividing them, we get the same result. So you can construct as many vectors as you like, and you can find the angle between them using this geometrical approach, and then you can check it using to see that the dot product is valid. If you do that several times, then you've basically got a kind of proof by induction, if you like. So there's that. That's a way of doing it. If you want to see another proof of this, there's a nice one using the law of cosines, yeah, which give you a geometrical proof of the dot product. But that just proves it as well. If you just plug in enough vectors, you'll see that the angle between them can be found this way and that way. So that proves that the dot product is a valid way to find the angle between two vectors. But it's also very useful for other reasons, which we'll go on to. So this vector here, if we project it onto B, so let's just drop a line here like that. So we're going to drop a right angle down here. Then this length here is A cos theta, if that's theta. So we got A cos theta. So that's that length there, if you like. A cos theta is this length, and then we're multiplying it by the magnitude of this vector here. So what we're actually doing is we're finding the part of this A vector, the magnitude of that actually lays in the B direction, yeah, and then we're multiplying it by B. So basically what we're saying here, the projection of A onto B, so the projection of A onto B is A cosine theta. I'm just repeating this now. And so the dot product, A dot B, represents the projection of A onto the direction of B multiplied by the length of B. This becomes particularly useful when one of the vectors is a unit vector, because a unit vector by definition has its size equal to 1. So if we want to find the part of this vector A that's lying in the k direction, you know, how much of that vector A, how much magnitude of that vector A is lying in the k direction, then we can do A dot k, and now obviously k is just 1, so the magnitude of the unit vector is 1, so we end up with A cos theta. So you can see that A cos theta is the same as, you know, if you've got the angle there, you can see that that's the projection on that line there is A cos theta, yeah? So what we're saying is the part of that A vector that lies in the z direction is A cos theta. Thus, to find the component of any vector in a given direction, you simply form the dot product between the vector and the unit vector in the desired direction. So that's kind of useful, you know, because I mean, for example, if you want to resolve forces, then you can use the dot product to do that. So you can find the part of the force that's going in the k direction. So that'll come in useful later. So just remember that it's a very easy manipulation. You can easily just plug in the values, find the magnitude of A, find the magnitude of B, and then you know that the angle there is the angle between them. And so you can just memorize that. I mean, and then when the problems come up, it'll make more sense. So for example, just to give you one example, one very simple example of using this with unit vectors. Since I dot I equals the magnitude of I times the magnitude of I times the angle between them. Now, I dot I, we know that if you dot a vector by itself, in this case if you dot I, which is going in the x direction, by itself, then obviously the angle between those two is 0, yeah? Well, you know that cosine 0 is 1, so that means that anytime you multiply I dot I, you get 1. And anytime you multiply any other unit vector with a unit vector that's 90 degrees to it, which you can say in this right-handed set, so if I multiply vector I with y, that's a 90 degree angle, so I'm going to get cos of 90 is 0. If I multiply I with k, I'm going to get 0 again, yeah? So that's why you get I dot j equals 0, okay? So that's kind of useful as well. Because when you multiply A dot B, you notice that you're multiplying I with I and J with J, etc. Yeah. So this gives you this shows you why you get the ones and the noughts. So that's kind of useful. So anyway, that's the dot product. That's basically a very sort of short outline of how it works, and you'll be using that quite a bit. So it's good to get the idea of how that works. The vector cross product gives us a vector in this method of vector multiplication, unlike the scalar product which gave us a scalar. So I'm just reading from the notes here just to make sure I cover everything. So what I'll do after I've read the notes is just explain so it doesn't sound so robotic. What we've got here is that the way we write this down is when we do a cross product, we write the vector A and we use a big cross. It's not to be confused with multiplication. This is the sign that says it's a vector cross product. Okay, it's not the same as B cross A. So whenever you see that, it's important which vector comes first. So in this case we've got A cross B. Now the easy way to figure this out to get our new vector, because these are two different vectors, and when we do a cross product we get a completely different vector. So I've just written out what you actually do get here. You get a component in the I, you get another component in the J, and you get a component in the K. The other interesting thing about the cross product, if you've got two vectors in the plane like that, you'll find that the cross product is perpendicular. So this is where the cross product comes in useful for electricity and magnetism. It's the fact that we can find a perpendicular vector to the plane, and that's quite useful thing to be able to do. So that's why we need to learn this. So how you find the A cross B is simply you write down this matrix. So what you'll do is you've got I, J and K, so you write them on the top, I, J, K, then you write down the coefficients of the A vector, AX, AY, AZ, then you write down the coefficients of the second vector. See, A cross B, now we're going to put the second vector underneath, BX, BY, BZ. So this is a rule, yeah, you only just got to remember this. And it allows us to get this just really quickly, yeah. So the way we do it is, first of all, we'll do each one in turn. So what we're going to do first of all is going to do the I. Now when we do the I, the rule here is we're going to loop around everything in the row that includes the I, and every column that includes the I. So we put a loop here and a loop here, so we can see we've looped that. Then we write down the I, and then we look at the components that are not looped, and that's these four components here. And what we do is we say, this is the rule. We go this times this minus this times this, and that's all you really have to remember. So it's quite easy to remember it. So it's AY times BZ, that's there, minus AZ times BY, minus AZ times BY. Now for the second one, J, we do a similar thing. We put a ring round everything that includes J in the column and everything that includes J in the row. But this time, for this one, it's a minus. That's important because we end up with a minus here for the J part. So that's important that you put that down. Okay, so that's not obvious, but you just put a minus there. And what it means is that you've looped those. Now you've got the same thing again. This time you've got these four components, AX, BX, AZ, BZ showing. The rest have been covered with these two loops. So we go AX times BZ, which is that one, minus, so we've got minus here, AZ times BX, AZ times BX. That gives us the second component here, as you can see. That's the second component here, AX BZ minus AZ BX. Okay, finally for this one, what we do is, and I haven't written it down just to save a bit of room, is we cover that column this time and that one. And here we've got, you can see now we've got these four components left, AX, AY and BX, BY. So you can see here it's AX, this diagonal here, we start always with the top left diagonal, we go AX times BY, so that's there, and then we subtract AY times BX, so that should be a subtraction there, so made a mistake there, that should be a subtraction. And just correct that. So it's the same thing. So it's AX times BY and minus AY times BX, and that gives us the final one for K. So that's how you would actually solve that's how you solve this determinant to get the vector in the perpendicular to both the A and the B vectors. So if you've got an A and a B vector in this plane, then the cross product vector will be perpendicular to them. Yeah, I've drawn this down. I've just said this anyway, but from my notes, this vector here is A cross B. Yeah, so there's A and there's B. Also, to figure out which way it points, think of a right-hand screw. You always turn this screw from the first vector into the second. So if we're going A cross B, we're going to turn
we're going to turn that into the second. And if it's a screw, obviously it's going to come out. So you're screwing it out like this. So it's going to come up as it's showing up. If you was crossing, if that was B cross A, which is why it's important which one we place first. If it was B cross A, for example, and not A cross B, we'd be moving this way. So you can see if you're turning that way, then you can see that as you turn the screw, it's going down. So in that case, the vector would be down like that, as opposed to up like this one. So it would be going down. So that's how you can get the sense of the direction. Just imagine a screw and look at the first vector in here, and then in your mind just turn it to the second one and then think where the screw's going. Then you can figure out the direction of A cross B. So that's an easy way. That's the way I do it. It's really easy. So this formula, this part of the formula might not be very clear why that's equal, yeah? And now we're going to sort of show why it is. So here, I don't know if you can see, but I've dropped a perpendicular line from B down to A, okay? And then I've stuck, to show that it's a right angle triangle, I put an angle there. So between A and B, we've got an angle, and if we drop the perpendicular down, so the horizontal distance is the magnitude of B times sine theta, because remember, sine theta is the opposite, which is this side, divided by the hypotenuse. So if we know the angle, okay, we can work out the hypotenuse. So the hypotenuse then is the magnitude of B times sine theta, which is that part of this equation, okay? Now, the area of a parallelogram, as you might well know, is base times height, okay? So is height times base. I've actually not written off BAS for some reason. That's base. So it's height times base, and hence the magnitude of A, obviously that's the base length. So this magnitude of A is the base length. And then the height, so for this parallelogram, we want the height. So the height is B sine theta. Hence, the area of the parallelogram is the magnitude of A times the magnitude of B times sine theta. So that's interesting. So what we're saying is that the magnitude, when we find the A cross B vector, the magnitude of it is equivalent to the area of a parallelogram. Just memorize that as you memorize. Remember, the cross product uses sine theta, this is the way I remember it, and the dot product always uses cosine theta. And you can always remember it because the dot product, if you remember I dot I equals 1, then you know that for an angle between two unit vectors, when it's 0, then it has to be a cosine, because only cosine 0 gives you 1. So then you know that for the cross product, then it's not cosine, because that's the dot product. It has to be sine theta. That's the way I remember it, but you can just memorize it. It's quite easy to remember. With this rules here, due to the definition of cross products, you can take two vectors, A and B, and multiply with their above rules to obtain the top equation above. So here, for example, if you were to just take two vectors and multiply them using these rules, these cross product rules, in other words, I cross I, well, if that was I and that was I, then these were unit vectors. Unit vector crossed with unit vector, so I cross with I. Now you know that the angle between them is 0, so sine theta is 0, yeah? So I cross I gives 0, and J cross J gives 0, and K cross K gives 0. But I cross J gives K, okay? So you can see that if you think about where I cross J is, so if we just draw that, so that's I, and that's J, and that's K. Right, so if you're saying I, if you're moving the I vector across to the J vector, then you're coming out, so it's plus K, and J cross K, so if you're moving J over to K, then you're going like this with your screw, so it's coming out, so it's plus I, that's plus I, and then K cross I again, if you're going K cross I, so we're going, if you think of it like that, we're coming out of the page using the screw, so that's plus J. But here, this is the interesting one, you got J cross I. Now J cross I means you're going from J here to I, so look, you're spinning round that way, so you're going into the page, so that's minus K. and then K cross J. So K cross J, you can see if I put my screw here and I swing K around to J and start turning, then I'm going into the page. Well, I've defined I coming out here as positive, so that means it's minus I. And then finally I cross K, so if I move I towards K, so I'm going like that now, you can see if I'm moving the screw in that direction, then I'm going that way, so that's, I've defined the positive J in that direction, so we're in the minus J, so that's minus J. So you can figure all those out very easily, and with those known, if you use those as the multiplication rules, then if you multiply A cross B and use these rules, then you'll actually get this equation without going through the determinant. But as you can imagine, that involves like multiplying all the I's and the J's and the K's. So these rules were invented by mathematicians to enable us to solve problems where we needed to find a vector in the perpendicular direction between two other vectors in a plane, so that we could get a right-handed set. Yeah. Typical applications of cross products include, for example, torque problems where you've got torque times the vector r cross with the force, and magnetic force problems. So you've got a moving charge, you've got a velocity, a moving charge, and then you're crossing it with a magnetic field, and the force actually is perpendicular to where the charge is travelling, and the magnetic force it's perpendicular to those. So that's going to be useful for solving magnetic force problems, which is really I think probably the reason a lot of this stuff was set up to solve these problems. Yeah, set up back in the 1800s. Yeah, this maths was nicely utilised so that we could solve magnetic force problems, and also it's useful for fluid flow and other things.